Hey everyone, we are going to be doing our meeting here, which is on semantic similarity. Hey, hey Matthew, are you there? Matthew, are you there? Hello?
Hello. Hey,
Hey, what's up?
how are you doing?
Good. I'm not Mark, in case you
Yeah.
were wondering.
Okay. That
You're
was,
wondering, wow, Mark, you look and sound a little bit different. Yeah, I guess he's in Portugal, or at least on the way to Portugal. So,
okay. Great.
so yeah, how is everything going?
It's going all right.
Good. Well, we'll see who shows up today. I'm going to be talking about the semantic similarity
Okay,
stuff.
great.
So
Okay, can you hear me?
I hear you, William. How's it going?
Why is this not working?
I saw your question, by the way, about the task I gave you,
Mhm.
and I wasn't quite sure what that was. So we'll have to look at kind of take a look at that. Yeah. So
Okay. Yeah, I was looking. I think a lot of them were asking that same kind of question. So, but I didn't understand what it wanted. But I went through the labs and
okay.
saw some things that could be improved.
Okay, good, good. I'm glad to hear that. So, yeah, I'm not sure what the template is referring to. So I'd have to look at that. When you say template, is that talking about some kind of style template, or do you know what that is? Like,
No, I didn't know. That's why I asked you.
okay.
Is it
I
okay
don't
if
know
I
myself.
edit things, or do you want me just make notes?
Well, I would go ahead. If you see things that can definitely be improved, I would go ahead and edit it. We can always roll back your changes if there's a problem.
Okay, yeah, because I
So,
see
yeah.
something like maybe add a little more explanation of certain things.
So yeah,
Let's see it.
that's fine.
Okay.
Hey, Will, was there anyone over in that other Zoom meeting?
No, it was just me. It's
Okay.
it's possible, but yeah, it was just
Okay.
me when I wasn't there, so I didn't see anyone else. But I think we might have to like update, because like I think I used the link that was in the email,
Yeah.
so you might have to like
Oh.
send an email to everyone.
Yeah, let me.
Was there a confusion on the room here?
Yeah, because I think Mark put a link, and that's the one I went to on the email about the NLP seminar,
Mm-hmm.
and then Matthew just told
It's
me,
a
hey, Tim's in a
different
link.
one from the one that's in the the Google Doc, the one that you're using.
Okay. Well, maybe we should send out an email then.
Okay.
Let's see. Let me go ahead and send that out. Let me go ahead. Okay. Okay. I went ahead and sent that out.
Okay.
All right. Well, I don't know if others are going to show anyway. I went ahead and sent that out, but let's go ahead and get started with what I was going to talk about.
Okay.
That's okay,
Okay.
with everyone. I
Yeah,
am
that's fine.
recording it. So, all right. So, so what Mark asked me to do this on just like on yesterday. So I won't say I have everything kind of all together, but I think, one of the things that I want to talk about is actually the task I kind of had assigned myself in terms of this, which was the text similarity portion. And so if you remember kind of our flow for the semantic similarity problem is that, well, first of all, let's talk about what similarity means, right? So, so the term we usually use is called semantic similarity, right? So, and in fact, there's several different kinds of similarities. There's lexical similarity, which basically just means how close the words that we use are, right? And that's a lot shallower in terms of meaning, and obviously not what we're trying to do. And then there's a semantic similarity problem, and semantic similarity is talking about meaning. right? So, for example, actually, there's a reasonably good blog article. I'm going to go ahead and use that here. Let me go ahead and write that in the chat. Okay. And so it talks about this problem, I think. Now, I'll talk a little bit later about some of the approaches may not be the same as what this guy talks about because it's a little bit of an older article. But nonetheless, I think it defines the problem pretty well. Right? So, and for example, the guy here says that this phrase, the cat ate the mouse with the mouse ate the cat food. And on the surface, that does seem quite similar because many of the words are the same. But in fact, the meaning is different in meaning, right? So, so one of the ways that we are able to do this is we're able to develop vectors that can do that. Okay, so the first step of whatever we're going to do likely is we're likely going to generate some kind of word vector embedding, right? So, and we've talked a lot about that, right? So, in fact, you know, we've been talking about BERT and other approaches, and all that has to do with the BERT vector embedding, right? So, but there's another important part of this is, so, okay, so once we have a good embedding, right? Then what are we going to do? We need some kind of way to measure the similarity between the two vectors. Okay, so there's some different approaches in what we talked about. And actually this guy mentions a few different approaches and actually gives kind of sad faces and happy faces according to which ones that he thinks work the best in terms of performing similarity at the sentence level. Okay, now the first way he mentions, which apparently he's not a big fan of, is Jacquard similarity. So Jacquard similarity is actually a similarity metric which is mainly used in text mining problems. And actually we could probably just use Wikipedia to go and look that up, you know, but it is, okay. So it is, let's see if we actually talk about that specifically about here. So it's actually talking about it here in terms of kind of the intersection and union of sets, right? And so the idea here is that we look here at this metric here of the intersection of A with B over the size of the union of the sets, right? So it's a fairly simple metric and one that is used a lot in terms of text mining type of problems, right? So, so the idea then is that it gets us a similarity metric. Okay, so there are other ways that we can do it. We could use k-means clustering. So basically the idea is that looking at the relative difference between two vectors in terms of their cluster identification might be another way. Cosine similarity. Now, cosine similarity is probably sort of the baseline metric that we tend to use in NLP, right? So cosine similarity simply means that we are going to, so actually, and this article actually, it talks about, first of all, Jacquard similarity is talking about this in terms of the size of the intersection divided by the union, right? Okay, we also talked about this clustering here. Cosine similarity, again, is probably, if you had to guess as far as kind of the basic approach that you might use cosine similarity. And what cosine similarity does is that we basically take the vector and simply find the cosine of the angles between the two vectors. Now, one of the reasons why we like cosine similarity is the fact that the cosine of the angle doesn't really depend much on the magnitude. And that's generally good for NLP problems because we aren't all that concerned with the relative magnitudes of the two vectors, right? So we're more concerned with their orientation. And so that is, and if we use other metrics like the Euclidean distance would be very, very much dependent on the magnitude of the vectors. Now, in some problems, that might be really good. But in NLP, the orientation tends to be more important than the magnitude. So, so I'd say cosine similarity is again, he is at a sad face, but it is probably kind of, I would say, our sort of our baseline metric that we're likely to want to use for looking at that. So a simplistic approach, and one that we did when we did this before, was to take the BERT vector and simply find the cosine similarity. You find the cosine similarity, and you now have some measurement of what the vector is, right? So now, in this article, they talk about using various vectorizers like the count vectorizer from scikit-learn, which is basically an implementation of the TF-IDF. Actually, it's really not even TF-IDF, it's more TF, right? So, and he talks about how you can use a pre-trained method such as GLOVE plus the cosine similarity, right? So, right. So those are all kinds of methods that we can use. Okay, now, with kind of more traditional text mining, one of the problems that we often come up with is the fact that vectors tend to be pretty highly dimensional, right? So, and when you use TF-IDF, they can be very, very, very highly dimensional. And so that makes similarity a problem. So in practice, when we're using like TF-IDF, we don't tend to actually find similarity directly against the vector. Normally what we want to do is we want to reduce dimensionality. Now, the thing about BERT is that we don't actually have to reduce the dimensionality because the dimensionality is already specified as one of the hyperparameters of the BERT model, right? So we specify the dimensionality. However, with TF-IDF and some other kind of vectorization methods, that's not necessarily the case. So because of that, we usually apply a methodology called latent semantic indexing. And so latent semantic indexing basically just means is that we're going to take a bag of words vector, and then we're going to do dimensionality reduction against that to turn it into basically from a very highly dimensional sparse vector to a lower dimensional dense vector. And to do that, the basic approach is called LSI, or latent semantic indexing. And the reason why we do this is because the cosine similarity distance and other similarity distances tend to work better with dense vectors that are smaller dimensional versus sparse large dimensional ones. And if you think about it, it kind of makes sense, right? In a sparse vector arrangement, you have thousands or even more than thousands of dimensions, most of which are exactly zero, right? So so if we're going to find the cosine of angles between them, now we have a cosine of an angle of a many thousand dimensional vector, but 99% of the dimensions are zero. So that is a bit problematic when it comes to the problem. So by reducing dimensions using LSI, we can usually get a better approach. So that's called LSI. Now, as I said, LSI isn't probably needed in many cases, and probably not in our approach, because if we use a BERT vector embedding, Mark's texting me here. Okay. All right. So one of the problems here that this guy mentions is the fact that if we're using a bag of words approach, then if they don't have any common words in the text, then the cosine distance will be exactly 0. It has to be exactly 0 because it won't have any. So that is a problem because there probably is some, in this case, there is actually similarity. So there's an approach here called word movers distance. And basically what word movers distance actually is it takes this, rather than takes the words themselves, I'm sorry, the sentence themselves in terms of words, what it's going to do is it's going to do a vector transformation of each word and then do that vector transformation in word space. Now, this is going to be useful if we're going to use a word-based embedding approach like word2vec or glove, right? So if we use word2vec or glove, then what we can do, now word2vec or glove is going to give us word similarity. Word similarity and sentence similarity, of course, not the same thing at all, but we can use those kind of things in order to help to understand that. So in this case, what we're doing is we're creating vectors for each word. And then what we're doing is we're measuring the distances of each word to movement. So that's called the word mover's distance or the earth mover's distance. And it's a little bit of a similar problem to what's called the transportation problem, which is basically a type of common problem, one which, by the way, is kind of famously difficult to compute, is how we can optimize the cost of moving transport of a large volume to another. Okay. So there's a number of different ways that we can do this, right? So again, the distance here, though, is based on a word vector embedding approach. We'll talk about this. Okay. So, okay. So another intriguing way to look at this is called a autoencoder. Okay. Now, an autoencoder is a neural network-based approach, which is used a lot for unsupervised machine learning. Now, basically what an autoencoder is trying to do is the autoencoder is trying to create, well, there's different kinds of autoencoders. But basically autoencoder means that we're trying to learn a way to encode data, right? Now, there's different ways that you can do an autoencoder. Some autoencoders are designed to encode the data in some kind of more compressed format. That's what we're going to use here. Other kinds of autoencoders actually are designed to encode the data in more dimensions than the original one. So what we're looking at here is called under-complete autoencoder. And there are also over-complete autoencoders, which are, the design there is kind of like for learning kind of feature generation and that kind of thing. Now, the idea here is that we are going to try to learn some kind of hidden encoded representation of data. And then we're going to use a decoder to learn the representation. Now, why do we do this? Well, it's not, as you might think, to develop like a great compression algorithm. That's not really what it's for. Rather, the idea is that we're going to try to come up with a useful hidden or set of variables that we can use for this. So it's used a lot for unsupervised machine learning because those hidden features that we're able to do can then be done on any problem, right? So a good example of a place where a variational autoencoder would be useful would be dimensionality reduction. Or not, well, yes, it does dimensionality reduction. What I meant to say is anomaly detection. Anomaly detection would be a great example of where a variational autoencoder would be very useful. And the reason why that is that we would be learning a hidden representation of our, a learned hidden representation of our data. Now, the reason why that's useful for anomaly detection problems is the fact that an anomalous data would normally have a dramatically different compressed version than the ordinary ones. So the distance of that one would be very large. And that is one way, in fact, that we can use neural networks for anomaly detection. And anomaly detection is basically a unsupervised problem. Now, our similarity problem is also an unsupervised problem. We are not going to, well, actually, we could do it supervised. I mean, in fact, our glue task does exactly that. But at its heart, what we really want is we want a unsupervised problem, right? So what we want is we want to be able to take our vector and we want to be able to try to find vectors that are similar to that vector. We are not going to probably have enough data in order to, we're not going to have enough data in order to practically speaking, be able to come up with enough examples. Hang on for a second. Okay, so this idea is actually a good one. What we can do is we can come up, and the idea then is that we will use the variational autoencoder to make a latent vector. And then what we'll then do is we'll then be able to create and use this as a similarity measurement. Okay. Now, there also, it's here it talks about pre-trained sentence embedders. Well, of course, BERT is exactly that, right? So we'll talk about that a little bit more. Now, there are a couple of sentence embedders, though, that are worth considering that are specifically designed for this problem. So there is InferSent and there is Google Sentence Embedder. So InferSent, now we haven't really talked about these. The Google Sentence Embedder is actually a transformer-based architecture in some ways similar to BERT, but it is actually designed specifically for similarity problems. Now, that might actually be something useful for us to consider, albeit sentence encoder actually predates BERT by quite a bit. Facebook also has another similarity sentence encoder called InferSent. Both of them are for this kind of problem here. Okay. Now, there are other, so going back to similarity metrics, the Siamese Manhattan LSTM is another network specifically designed for similarity kinds of problems. In this case, it is interesting because so first of all, let's talk about what Siamese Manhattan means. Manhattan is just simply a distance measurement. And basically it's called Manhattan because basically you find the distance measurement by using the reason why it's called Manhattan is that you imagine you're in New York and you're trying to get from one place to another. So you have to walk along square grids, right? You can't cut through the block in New York because there's a building in the way. You can't do that. So you have to do that. So that's why it's called the Manhattan distance. So the idea is that it's imagined that you were trying to get from one address to the next in Manhattan. So you would walk along square blocks. So now Manhattan distance is often used in terms of NLP problems because it often does perform well. So although the distance is not dramatic. Now, what this case here is they're using an LSTM model for trying to, an LSTM model for trying to measure the distance, right? So in fact, they're using two LSTM models. That's what the Siamese part means. So, the approach here then is we're going to use a learned neural network in order to do the distance measurement. Okay, so that's an interesting approach. Number 9 here he's talking about is using BERT with cosine, which is exactly the approach that we have been using so far. Again, so we know about BERT, etc. So this is something we do. However, again, instead of cosine, we could instead use some of these other approaches that we're talking about. Okay. Now, there's also a set of approaches called knowledge-based measures. And knowledge-based measures are using semantic networks. So this is somewhat of a different approach. Knowledge-based measures is basically, instead of using a mathematical distance between vector, what it's going to be using is it's going to be using a graph-based metric. So, the idea then is that we would come up with the distance based on a distance in a graph here rather than the distance in the vector, right? So this is a little bit of a different approach, actually. So, again, one way that we could look at this is we could look at taking the vector of each word and then calculating distance in the graph. So, okay. So that's what this article talked about. Now, since this article has been written, there's been a few other approaches that are worth considering. So one of which is this one. It's called FAISS. I think it's pronounced FACE. It's actually produced by Facebook. So FACE is actually designed to essentially solve this problem, which is similarity function, right? So, so the idea is that one of the biggest problems with similarity is the fact that regardless of however we do it, it's going to be relatively expensive to calculate similarity if we get to very large data sets. And that's true regardless of what type we use. One of the reasons, in fact, why the Manhattan distance is popular, is the fact that Manhattan distance is actually relatively simple computationally to compute. The cosine similarity actually is not that difficult, but it's computationally a bit more so. This library actually is designed to help give you a fast and efficient similarity metric for very large numbers of vectors. So it's called FACE. Okay, so within Hugging Face, so within here we have our transformers. Okay, so we have some classes in here for similarity as well. So now the basic similarity that most of these is going to use is going to be like cosine similarity, etc. But we could also use, by the way, another one that's not mentioned in the previous there, but is worth considering are statistical measurements using correlation, like Pearson correlation coefficient, Spearman, et cetera, right? So that's actually another whole class of similarity metrics that we can also use here as well. So yeah, so that is pretty much all I have actually. So the approach that we're using, so let me just talk about so the approach we're using basically is we're still kind of like looking at this using the cosine similarity, right? So that's kind of what we've been doing. but it's worth considering if there are maybe some other approaches that might be A, faster computationally, like look at something like face here, or B, more sophisticated in terms of their similarity metric. Like, for example, some of the ideas we talked about before, like using LSTMs or autoencoders and other things like that, right? And so those are things, honestly, I haven't really looked too carefully at, but those would be some approaches that we could look at. So, all right, so that's it. So I don't think, did anybody else show up? Oh, yeah, I guess there are a few. So let's go ahead and take questions here. Oh, by the way, did I ever share my screen?
No, you did
I
not.
did.
No.
Oh, I'm sorry. It would have been a much better presentation had I done that. That was stupid. I'm sorry, everyone. So anyway.
Yeah, I've been just like using the. I think you shared us links, and I was trying to follow along.
Right. I apologize. I thought I was sharing my screen. I'm kind of absent-minded with this kind of thing. I apologize. Oh well. Anyway. Okay.
I was curious just about this face because I haven't heard about it yet before. So you're thinking about
Okay.
maybe implementing this with BERT somehow, so it makes it much more. I guess.
Yeah. Good question. So that we could definitely use it with BERT. So in fact, it would be so it could be used with any vector, right? And so the bottom line is that the output of that is just going to be a vector. And we could certainly use BERT or anything else with that, right? So basically face is just a C++ library wrapped in Python wrapper, right? So, and it is designed, of course, it's to be used GPU, CUDA, and all that. So yeah, I mean, we could use it with any vector library, right? So including Hugging Face or whatever other kind of transformer we wanted to use, right? So the idea behind it is that it's really designed to make it efficient to do a similarity on very, very large sets of data. In our previous rev of this, we were using the nearest neighbors distance metric from scikit-learn, right? So we all know scikit-learn is going to have very limited scalability, right? Because it wouldn't use GPU at all, and also we would try to perform everything in memory, making that highly not scalable, right? So something like face would be a far more scalable approach, and one that we should probably consider. Although I believe that the Hugging Face also has its own cosine similarity functions, which, again, I would imagine would themselves be much better than scikit-learn. But yeah, looking at that, again, I've actually played around with Face a little bit, and it looks interesting, especially if we are going to use, similarity among very large data set, right? Because like if you had several billions of different data points that you have to calculate similarity, well, that's a pretty expensive operation, right? So, so finding an efficient way to do that would be important. So just out of curiosity, my question from my side, has anybody looked at let's say unsupervised semantic similarity and use a different approach other than what we've talked about in this presentation? Because I'm just kind of interested to know, I feel like, we all probably understand cosine similarity pretty well, right? But is there any kind of other approaches that anybody here listening to the presentation might have used or anything like that? Yeah, so.
Yeah, I haven't looked at it too much besides what you have just described. What are some of the other common approaches besides the ones you just talked about?
Well, okay, yeah. I mean, basically, what I've tried to describe, I think, is kind of a kind of, I think, a pretty good summary of what's done there. Now, one thing we haven't talked about is approaches that might involve topic modeling and other things like that. I mean, that's a little bit of a different approach, right? But that is another way that you could look at similarity, like in terms of topic model, relationships could also be a way that you could look at similarity. And then, so like the GenSim library, for example, is basically full of different approaches, albeit not mostly deep learning approaches, to trying to solve the similarity problem, right? So let's see. How do I share my screen, actually? Maybe I can stop my video. Here we go. All right. Right, so if we look at GenSim, this is a library that I have a lot of experience with. Right, so there is, topic modeling based approaches there. That's kind of sort of one of GenSim's kind of specialty, but also there's a number of similarity queries that are performed there as well. Now, that said, GenSim is primarily going to be focused on kind of bag of words type, kind of bag of words kind of types of approaches and that, right? So we're kind of taking somewhat of a different approach. But yeah, there's definitely a lot of different, ways we can do that. There's also, of course, supervised methods, right? So supervised methods are going to mean similarity based on simply training regression models. In fact, the glue metric of semantic similarity that we've been working with, the STSB, that's a supervised machine learning method, right? The problem is I'm not a big fan of supervised machine learning methods just because I don't think we're going to be able to really be able to create. I think it would work great if we had enough human annotated data, right? If we had enough human annotated data, then I think that could be an interesting approach. But the problem is that we would need a very large amount of data of human annotated similarity data based on the type of data that we wanted to do. So in the case of we're doing legal documents, we would need somebody to basically generate a whole bunch of sentence pairs and then give some kind of semantic similarity score to those sentence pairs, right? That's what STSB does. And that I think would be great, but the problem is that I can't think of any way to get enough data with a reasonable budget. Of course, we don't have any budget, right? So of human annotated similarity data, it would have to be, you'd have to have a big corpus of that. And it really ideally wouldn't want to be a generic corpus, but one very tightly tied to that. The STSB data only has thousands, not millions of examples. And so that is in no way adequate to create like a reasonable model, right? So I mean, supervised learning models for similarity, that could also be effective. But I think the problem is just, the acquisition of enough data, and you would need millions and millions of training examples to really make that work. I mean, even more than billions. I mean, you need really big really big annotated data sets of this, and to make this really effective. And so I think that could be very effective, but I just don't see a way for us to move forward with that. But let me open that up. Maybe I've misjudged that. Anybody have any experience with that, or with kind of doing supervised human annotated similarity type modeling? Okay, we'll take that as a no. All right. But a good question there, William. Good question. All right. Any other questions?
Hi, Tim.
Yeah.
This is Kabay. Sorry, I came in late. I missed like most of the presentation. Will you be able to share? If you have a PowerPoint, will you be able to share it?
Yeah, actually, I was mostly going through somebody else's blog article, so I'd be happy to share that. I did, unfortunately, I kind of absentmindedly forgot to share my screen, and everyone was too shy to point that out to me. So we do have a video, but unfortunately, it's basically just going to be audio. But if you want to listen to my audio, we'll definitely make that available too. So.
Cool. Thank you.
I think they also kind of like coordinate with the links that you showed us, right? If I'm not mistaken. So it'd be good to like share those links.
Right. The link I gave you, I followed that pretty closely. I honestly, I didn't have enough time to make my own slides, although this is the important thing. But I felt like the guy in the blog article did a pretty good job of explaining at least kind of the various approaches. And you notice that, his, again, he only kind of mentioned BERT kind of belatedly at the end, right? But I think overall, it kind of talked about the different approaches. And the thing is that, I wasn't really trying to cover like the sentence embedders here, right? So, I mean, we know all about various kinds of sentence embeddings. We talked about that. But we're talking about like, what do we do with a vector after we do the sentence embedding? That's what I was trying to focus on. So, yeah. For the semantic similarity problem. That's what we're trying to focus on today. Yeah, so.
So Tim, do you, for either a unsupervised or supervised approach, your
Right.
embedding strategy is pretty much the same, right? Because you
Yeah,
have to
pretty much.
embed.
I mean, now it is worth mentioning that we did mention there are some embeddings like Google's universal sentence embedder, which are specifically designed for similarity queries, right? So, so in fact, you may want to consider, kind of tuning your model and or your approach for embedding based on the fact that you want to do a similarity query, right? So that's something to consider. But yeah, basically at the end of the day, right, you need a transformer and the transformer creates a vector. And that part of it, is going to be one thing, right? So we've been talking about using BERT or some variant of that. And then once you have the vector, then it's time to find how vectors are similar, right? And so, so there's, in some ways, there's two kind of somewhat independent steps, right? We're creating a transformed vector, and then after that, we are using some kind of similarity metric or model in order to determine how those vectors might be similar, right? So.
Okay, great.
Yeah, and so. And that the simplest thing would be what we've been doing so far, which is cosine similarity. Cosine similarity isn't really a machine learning model, though, right? There's no real learning to it, right? So, I mean, of course, the BERT part has learning, but so so when we say, like, in that sense, we're saying it's kind of like unsupervised, although it might be closer to fact to just say it's not really a machine learning model at all. It's just measuring the similarity between the BERT vectors. Right. And then, we talked about maybe some other ways that we could try to do a unsupervised machine learning model for having the similarity. Yeah. So.
So Tim, I actually have some comment. That's actually something I've been thinking about BERT. I don't know if it's correct, but I'd like to share. And if I'm wrong,
Yeah.
just let me know. So I'm working on a oil and gas project. So
Okay.
it's an LP project. So I'm using BERT as the pre-trained model, right? And after we got excuse me, and after we got some like thousands of on the level of thousands of annotated oil and gas text documents, we're gonna feed those into pre-trained BERT and do 5 or 6 epochs of training, of fine tuning, and got the embedding of the word, right? So I'm thinking I'm just thinking how can you do this like unsupervised? Because to me, I understand BERT without any fine tuning is like it's like a person with a general knowledge of the human language, and then
Right.
given it annotated training data for fine tuning is like you just assign a major to it, like whether it's oil and gas or legal, right? Get it familiar with the terminology you use, and then you can ask the particular question in that particular industry. So that's what I had in mind, and I don't know if that's correct. Yeah.
Right. So what you're talking about is you're talking about fine tuning of the BERT layer embedding, right?
Yes.
By the way, actually, just a quick heads up: these meetings actually expire after an hour, and that hour is probably coming up in a few minutes. So just to give everyone a heads up that we'll just run to the end, but just it may happen abruptly. So, yeah. So when I was saying unsupervised, I wasn't actually saying that would exclude fine tuning of the embedding, like the BERT or transformer embedding. In fact, that would probably be a very good idea to do. The only thing is though, is that once you have a trained and fine-tuned BERT, and of course, to do that, you would need some human annotated data in order to perform the fine-tuning task, right? Because
Yes.
the fine-tuning task is basically like a semi-supervised task, right? So you need some human annotated data to do the fine-tuning task for sure. So when I was talking about unsupervised, though, what I was talking about is the similarity task, right? Which kind of comes after you've created the embedding, right? So now that we have this, this embedding, right? Now we have to find similar documents, right? So now the choices of there could be either a supervised or unsupervised method of finding the similar documents, right? And the problem with having a supervised approach is just that it's going to require you to have a very large corpus of data in order to find similarity, because you would have to basically have that data reflect every way in which sentences can be similar, right? Or not. And that's just a very, very large amount of, it's kind of cursive dimensionality in action there, right? So that's kind of the challenge. But yeah, I guess to answer your question though, that fine tuning of the BERT layer, that is another thing. And of course, that's a very good thing to do. And so when I say unsupervised, I'm not saying that it's unsupervised in the sense that you would not fine tune your BERT layers. I'm just saying though that the similarity model itself might be unsupervised, or it might be supervised, depending on your approach, right? So.
Okay, I see. Gotcha.
Does that make sense?
Yeah, it does. Yeah.
So sometimes I've been saying unsupervised when I talk about things like cosine similarity, but in fact, actually, that may not be totally accurate, right? So because cosine similarity, it's not really supervised or unsupervised, right? It's just a kind of a distance metric.
It's not really machine learning, or
Yeah. So, however, we could replace our cosine with either a supervised or unsupervised model for determining similarity, right? So, yeah.
Yeah. Okay, cool. Yeah. Great.
Any other questions, comments? All right. Well, I think we're about to run out of time. So I apologize, by the way, about my screen share fail. So anyway, so this should be being updated to the cloud. So I know, several of you asked about that. So we'll try to get a link for that once the recording is done. So.
Thanks, Tim.
All right.
Thanks a lot,
Thanks,
Tim.
everyone.
Thank you.
Okay, thanks. Okay, bye.
Charlotte is the name of the city. Charlotte.
Okay. Hey.